Chem activity number 5, part 2, we're going to look at the intermolecular forces that exist between molecules, and in particular we're going to start off with London dispersion forces. In my opinion, London dispersion forces are the most important, as they are the most ubiquitous. They exist in all molecules. To examine London dispersion forces, it's instructive to look at the data that's found in the table under teaching model number 2. We have two homologous series represented. We have the alkanes and the alcohols. Now, homologous series means a series of compounds that differ by a CH2 group, and therefore going from propane to heptane, the molecules are getting larger and larger. Going from ethanol to heptane 1-ol, they're also increasing in size. We can also see that we have the molar mass, the dipole moment, the boiling point, and the water solubility. I'd like you to focus on, for right now, the molar mass, dipole moment, and boiling points. Clearly, going down a homologous series, the boiling points are getting larger and larger. Now, why do we represent boiling points here? Well, remember that boiling point essentially represents the temperature at which the liquid particles possess sufficient energy to completely vaporize, to go from the liquid state to the gaseous state. To completely vaporize, the forces of attraction between liquid particles have to break. This means that at the temperature of the boiling point, the molecules have sufficient energy to break these forces of attraction. Boiling point is an indirect measure of the force of attraction between molecules. The higher the temperature of the boiling point, the stronger the force of attraction between molecules. So in a sense, going down a homologous series, we can see that the intermolecular forces are stronger and stronger. To understand why this is the case, let's go down and look under the information. First of all, under the information, we have that the boiling point, of course, increases as the force of attraction between molecules increase. And these forces of attraction we can call the intermolecular forces. We can also see that the most common intermolecular forces are the London dispersion forces. Now, although they are the most common, these are perhaps the hardest forces to understand. In the previous activity, we talked about the fact that molecules can be polar, and this is the result of a permanent dipole in a molecule. Well, London dispersion forces are the result of attraction between temporary dipoles. In chemistry, in a sense, all forces of attraction are related to the attraction between plus and minus. In the case of London dispersion forces, they're due to dipoles that exist, one temporary, and at the level of femtoseconds. So temporarily, even a nonpolar molecule can have an uneven distribution of electron density. This is because electrons are polarizable. That is, they're not static. They slosh around a molecule. So temporarily we can have an uneven distribution of electron density. But this is, in a sense, this uneven distribution of electron density is not predictable. It's on one side of the molecule, and then on the next side you're going to have an uneven distribution of electron density. Temporary dipoles, in a sense, depend on how large the molecule is, which is related to how polarizable the electrons are, as well as the surface area. An indication of how large a molecule is related to its molar mass. So in a sense, the molar mass is an indirect measure of London dispersion forces. So given this, let's go back up and to look at our data here. We can see that in a homologous series, going from propane to heptane, the molar mass increases. As the molar mass increases, the London dispersion forces increase. As the London dispersion forces increase, the boiling point increases. And so molar mass is directly related to boiling point. Now, comparing alkanes to alcohols, we can see that the alcohols have also dipole moments. But the dipole moment in this case is not related to why the boiling point increases. We can see that the boiling point increases essentially because the London dispersion force increases. Now, one of the things I also wanted to point out is going from ethanol to heptane 1-ol, we can see that the dipole moment essentially is measured at about the same. This is another sort of indication of how dipole moment is not a perfect representation of polarity, because I would say that heptane 1-ol is by no means as polar as ethanol is, because heptane 1-ol has a large hydrocarbon section to it, although the dipole moments are measured at the same rate. So we can see that this table represents the relationship between molar mass and boiling point, and essentially is a function of London dispersion forces. Now we will talk about water solubility later, but let's explore London dispersion forces a little bit further. And to do this, let's look on page 22, where there's an interesting question about a series of molecules that are related by the fact that they are constitutional isomers. Now, later in the course, we'll review isomers, but I think you might be able to guess what we mean by constitutional isomers, in the sense that if you look closely, all of these molecules have 1, 2, 3, 4, 5 carbons and are hydrocarbons, and therefore they have the exact same molecular formula. So these constitutional isomers have the same molecular formula, and the molecular formula happens to be C5H12, but they do differ clearly in structure. They also differ in boiling point. Now, a minute ago we said that the boiling point is a reflection of the strength of intermolecular forces. And so although they have the same molecular formula and therefore same molar mass, they do have differences in intermolecular forces. So how can this be? Are their London dispersion forces the same? Well, apparently not. There are no other forces. These molecules are not polar. So why would the London dispersion forces be different? Well, let's go back to the previous page, and you'll see that the London dispersion forces are related to the size of the molecule, but also the surface area. So you can see that the structures here have different surface area. The more linear the structure, the greater the surface area. And one of the ways to represent this is, even though I know that the bonds can rotate around, if we look at 1, 2, 3, 4, 5, this is pentane. The way I've represented pentane, this is its, in a sense, most stable conformation. And we can draw a second pentane molecule, and remember that intermolecular forces are the force of attraction between one molecule and then the second. Well, this linear structure has a substantial amount of surface area such that one molecule can be easily attracted to the second by London dispersion forces because they have a substantial surface area. By contrast, if we look at this molecule at the end here, which consists of a chain of 3 carbons, and we have 2 methyl groups on carbon number 2, so this would be 2, 2 dimethylpropane. This molecule is more spherical and in a sense has less surface area. So if I draw a second molecule of this 2, 2 dimethylpropane and realize, well, the intermolecular forces are still going to be London dispersion forces, but they're not going to be quite as strong in holding one molecule to the second molecule. There's less surface area to make the contact. One of the important things to remember about London dispersion forces is they are short range intermolecular forces, and therefore they're going to be maximized by having substantial surface areas. I'm just going to draw a second one here. 3 molecules, great surface area, great contact, same molar mass, but stronger intermolecular forces. And that's reflected in the boiling point. So you can see the boiling point for pentane is 36.1, whereas the boiling point for 2, 2 dimethylpropane is only 9.5. Now, when students are introduced to this idea that surface area has an effect on London dispersion forces, sometimes they have a tendency of wanting to focus a lot on the surface area. I would like to point out that surface area, while important, should be considered in a sense as sort of the last difference. Make sure that you first of all compare the molar mass, that is the size of the molecule, and then if the molar mass is the same, then consider whether or not there are differences in surface area. Our molecule that's found in the middle, which is the 2-methylbutane, would have intermediate surface area, and it has an intermediate boiling point, intermediate London dispersion forces. So the first thing to consider is the size of the molecule is related to its molar mass, and then the next thing is compare their surface area. So to answer the question that's given here, given that all of these isomers have identical molar mass, what features in the structure lead to differences in boiling point? Well, the difference is that pentane has greater surface area. Having greater surface area will have stronger London dispersion forces and therefore a higher boiling point. The last thing that we'll look at in Chem Activity number 5, part 2, is question number 4. Here you're asked to compare pentane and butane-1-ol, and specifically you're asked to indicate whether or not the differences in London dispersion forces can be used to explain differences in boiling point. Well, what we need to do is go back to the previous table and look at data concerning these molecules. So you're asked to compare pentane, which has a molar mass of 72 grams per mole, to butane-1-ol, which has a molar mass of 74 grams per mole. Now the boiling points are considerably different. 36 for pentane and 118 degrees Celsius for butane-1-ol. So clearly butane-1-ol has stronger intermolecular forces. Now we notice that the molar mass is greater, and you might want to use the argument, oh, it has greater London dispersion forces. But a difference of molar mass of only 2 grams per mole is not really sufficient to really indicate that there's a greater London dispersion force. If I wanted to use an argument of greater London dispersion forces, I'd be looking for a difference of molar mass of 5, 10, 15 grams per mole. But 2 really isn't sufficient. So I would essentially just ignore that difference in molar mass and realize that there must be something else at play that would explain this significant difference in boiling point and therefore significant difference in intermolecular force. And so back to the particular question here. Question number 4, it says, consider pentane and butane-1-ol. Can the differences in London dispersion force be used to explain the differences in boiling points for these molecules? The answer is simply no. However, of course, we need to go a little deeper, and that will be the topic of part 3 of Chem Activity number 5, where we'll investigate dipole-dipole forces and hydrogen bonding.